Okay, I think it's time to start. Welcome everyone. Today's the seminar today is given by Younghun Hong from Chung-Ang University, and he will talk about a famous problem about Fermi-Pasta-Ulam system. So please, Younghun, start.
Okay. Thank you very much for the introduction, and I would like to thank the organizer for giving me this nice chance to present my work to global audience, in particular in Asia and Pacific region. So today I will be talk about the KdV limit for the Fermi-Pasta-Ulam system. This talk is based on joint work with Chung-Ang from Ewha Women's University and Chung-Ang from Chungbuk National University, and they are Koreans. And also, I would like to mention that this talk is also influenced by collaboration with two young Japanese researchers, Shohei Nakamura in Osaka University and Yukihide Tadano in Tokyo University of Science. But before getting into the main subject of this talk, I would like to briefly introduce the problem I got interested in recent years. That is the continuum limit problem. I mean, it's slightly broader sense, because the problem is very simple and natural, but I think it is pretty as popular for mathematical society. Okay. Sorry. So let me introduce the continuum limit problem first. Later broader sense. So here we consider an infinite cubic lattice HCD. So it's like this. So it's an infinite cubic lattice whose mesh size is H, and a function U is defined on this lattice domain. And at least formally, as H goes to 0, this lattice points would cover the entire space. So we are considering this kind of situation. Okay, and on this domain, we may define discrete differential operator or difference operator as the fraction in the definition of derivative before we take the limit. Okay, and we also we can also define discrete Laplacian operator as a difference operator like this. Okay, and then using these differential operators, we can introduce difference equations on the lattice domain, HCD, infinite lattice. It can be anything, including the heat equation and linear Schrödinger equation and wave equation, and so on. And we can also add some nonlinearities to these equations. Okay, and in this setting, a natural question would be the following: can we show convergence from a solution to this difference equation to a solution to the corresponding PDE on RT as H goes to 0? But in order to formulate this kind of problem, we need a way to transform a function on a lattice into a function on a whole space. And probably the simplest way would be the linear interpolation. I mean, by linear interpolation, we mean that we just connect the graph of UH by straight line like this. Okay, and then the question can be visualized as this diagram. I mean, we would like to compare the solution to the difference equation with the PDE solution, but after taking the linear interpolation. Okay. And there are several motivations on this study. The first one is from numerical analysis, namely the finite difference method. But perhaps one could criticize that this kind of problem is not closely related to the numerical simulation, because there are infinitely many points. So actually for the real numerical simulation, we need finite points, and we also need time discretization to save computational cost. But I would say that this kind of convergence problem can be a sort of preliminary step to consider this full numerical scheme. And another motivation is from physics. In solid state physics, hopping electrons on crystal lattice can be described by a difference equation on, for instance, GD with fixed H. But on this fixed lattice, somehow a small amplitude solution can be approximated by the PDE solution, and actually by simple scaling, in most cases, small amplitude limit problem can be translated into the continuum limit problem, and vice versa. So mathematically, these two problems are equivalent. So this is one reason we may consider the continuum problem. Okay, and there is a few other motivations from physics, and it includes the KdV problems from the Fermi-Pasta-Ulam system, which is the main topic in this talk. And there are several references for a class of dispersive PDEs. I mean, as I said, this kind of problem can be formulated for any types of differential equations, but I would like to be focused on a class of dispersive equations because my background is there. Okay, and there are several known results. I mean, continuum limit of nonlinear Schrödinger equation is proved, and fractional nonlinear Schrödinger equation is also derived as a continuum limit from a model equation on lattice. And as I said, perhaps finite lattice would be more closer to numerical simulation, but recently I finished some project on I considered some finite lattice problem with my collaborators as well, and hexagonal lattice can be considered as well. Yeah. Okay, and there are several references, and in this analysis, I mean, when we prove continuum limit problems in various settings, in many situations, the proof of continuum limit can be reduced. I mean, more or less can be reduced, essentially reduced to prove a good estimate for the linear flows, because in PDE, a rule of thumb is we may have a good estimate for nonlinear solution if we have the good linear bounds. Okay, and once we have more information about the nonlinear solution, we can use this additional information to prove continuum limit. So, for instance, so in the case of nonlinear Schrödinger equation, if we compare two solutions, discrete one and continuous one, by using the Duhamel formula. So this one is the Duhamel formula for the discrete equation, and this one is from the continuous equation. And if we measure this, so we may try to measure this difference. But after doing some manipulation, we can rewrite this difference as the sum of small error plus this integral term. And you can immediately see from this expression that if we have, because of nonlinearity here, if we have good bounds, good L infinity bound for the nonlinear solutions, then we can apply standard Granoff type argument to prove the continuum limit. Okay, so in that sense, proving good bounds for the nonlinear equation nonlinear solutions would be useful, but this can be essentially done by getting good bounds for the linear flows. And then how can we get a good linear bounds? So this is a class of, so we are talking about a class of dispersive equations. And for dispersive PDEs, actually, one of the fundamental, most useful tool would be a Fourier transform. And fortunately, on this infinite lattice, there is a Fourier transform. And actually, even if you have ever seen this Fourier transform before, but it looks, you can immediately recognize that this definition is very familiar, because it's a kind of reversed Fourier series. So this is the Fourier transform on lattice, and this is the inverse, but somehow this looks like inverse Fourier series, and this is the inverse Fourier transform for periodic function. Okay, and on the other hand, as h goes to 0, we can formally see that this Fourier transform on lattice would converges to the Fourier transform on RD. I mean, in consideration of Riemann sum. And for the inversion, we can see that as h goes to 0, formally this inverse Fourier transform becomes the inverse Fourier transform on RT. Okay, this is type CD. Okay, and using this Fourier transform, discrete Fourier transform, we can actually solve the linear Schrödinger equation by the standard way. I mean, we can write Laplacian operator as a multiplier on Fourier side, and solving this ODE involving this symbol, we can obtain an integral representation for the linear solution. So this is the standard way. But here, a key difference from the continuous case, the PDE problem, is that we have some trigonometric phase function rather than Cauchy squared, and it makes a huge difference because unlike Cauchy squared, this phase function may have 0. The second derivative of this phase function may have 0. So like this. But fortunately, when the second derivative is 0, the third derivative is not 0. Okay, so by the Van der Kolk lemma, we can get some dispersion estimate. But I would like to remark that this kind of decay estimate is different from the PDE case. And this is necessary. I mean, necessarily we have these different bounds because of this different character of the phase function. Okay, so as I mentioned, so in this analysis, when we prove continuum limit, it is important to find a suitable linear estimate on discrete setting, but it would generate an interesting set of problems in harmonic analysis perspective as well, because we may have some different integrals, oscillatory integrals. So in particular, we may encounter oscillatory integrals with a degenerate phase function. So for instance, Klein-Gordon equation, we have to estimate this kind of oscillatory integral, but in order to deal with this kind of integral, we need some deep theory in harmonic analysis on oscillatory integrals with a degenerate phase. Okay, and this is let me quickly summarize what I mentioned. So we introduced the continuum limit problems very briefly on HCD, and when we prove this, for the proof of continuous limit, in many situations, a core in analysis would be to obtain a suitable linear estimate, but we may have in discrete setting, we may have some different oscillatory integral. Okay, we may have to analyze oscillatory integrals. Okay, and then so this is the end of the brief introduction of rather general picture, and I would like to talk about the main subject of this problem, this presentation, Fermi-Pasta-Ulam system. Let me talk about a little bit of the history of the problem, although I'm not very familiar with this history, math history. So this is the history. So in 1950, early computer, MANIAC computer was built in Los Alamos National Laboratory. Okay, and four physicists, famous physicists, Fermi-Pasta-Ulam Chingo, had a chance to get access to this new machine. Okay, and they, for numerical simulation, they introduced a very simple nonlinear system describing 1D chain of vibrating strings interacting only with nearest neighbors. So this is the picture of their model, and precisely we can describe the model in this way. So actually, for Fermi-Pasta-Ulam system, FPUT system, there are many different settings, but in this talk, I would like to be focused on infinite chain case. So here, what I mean is that there are infinitely many strings, okay? And we label these chains by X. So X is the label of the strings. So for instance, this one, let's call this one is 1, and this one is 2, and this the next X there are 3, 4, and so on. And there is 0 on the left, and -1 and -2, and so on. Okay. So X is the label of strings, infinite on infinite chain, and Q and P are the position and the momentum of the axis string at time t, and V is the potential function. It can be more general, but in this talk, let's fix the standard. Let's fix the standard FPU potential. Okay, and then the model is given by this. So it's a standard equation. Derivative of position is momentum, and derivative of momentum is the force, but the force is given by this. So here the key point is that this force depends only on the nearest neighbor point. Okay. Okay, then they did some numerical simulation for this model, but however, when they did the numerical simulation, they expected that by some sort of chaotic interactions, nonlinear interactions, they expected that everything will be equally distributed. But surprisingly, at the time, it's 70 years ago, but surprisingly at that time, numerical simulation showed the opposite behavior. They found quasi-periodic motions in numerical simulation. And this is the picture of the numerical simulation I got from this book. So what it says is that if we insert initial data, single mode, if we insert single, like for instance, sine function then since this is the nonlinear dynamical system, we may expect, the single mode can be separated into many different sine or cosine functions with different frequencies. Okay, and at that time, these physicists expected that everything will be equalized. The energy localized in a single mode can be distributed to other frequency waves but numerical simulation shows that after a certain time, the localized waves coming back to at some point. Okay, somehow the energy initially localized becomes restored back to the original one. So likewise, there are some sort of quasi-periodic motion appeared. And this kind of phenomenon is known as the FPU or FPUT paradox at the time. And this puzzle actually had been solved by two physicists, Jabuski and Kruskal, by discovering the connection to KdV equation. And what they found is that it's very surprising. I mean, what they found is that if this kind of ansatz, where W plus and W minus are the solution to the KdV equation, then this ansatz actually almost solves this Fermi-Pasta-Ulam Jingu system, FPUT system, up to some small error in terms of age. I don't know how to do that, but they found this thing. Okay, and then there is some sort of mixture of the theory. I mean, I don't know which one is coming first or later, but in current literature, we can actually explain the quasi-periodic motion of FPU system. We can explain quasi-periodicity of FPUT system by the connection to the KdV equation. And there is, as I mentioned, there is a huge literature, and which I'm completely ignorant. But yeah. Okay, so this is what I wanted to say in this talk. Okay, so there is some connection, and mathematically, this connection is rigorously proved by Schneider and Wayne in 2000. And so basically, they proved that this difference between FPUT solution and this ansatz is very small for a long time. And actually, very, very roughly speaking, they proved this kind of theorem using a dynamical system approach. I mean, they very, very roughly speaking, they wrote an equation for this difference, they are, and then they wrote a difference equation for R, and then they found some suitable condition on initial data so that R remains small for a long time, something like that. Very, very roughly speaking. Okay, so this is a quick summary. So these four physicists introduced the Fermi-Pasta-Ulam Jingu system, and they observed quasi-periodic motion for their numerical model. And Jabuski and Kruskal discovered some connection between FPU system and KdV. And mathematically, Schneider and Wayne proved the connection rigorously using a dynamical system approach. Okay, and then we somehow, with my collaborators, Cheol-Kwang Kwak and Chung-Ang Yang, we revisited this problem using discrete Fourier transform and dispersive PDE approaches. And our principal aim was to relax some assumptions in the previous result. So here there are some complicated assumptions on the initial data, and we wanted to simplify some conditions. So conditions in this previous result, okay, by using some different toolbox. And for that, we have to we have to reformulate the problem so that we we can easily apply the dispersive PDE techniques or harmonic analysis tools. So this is the way we reformulated the problem. So let's recall that the FPU system can be written in this way for the displacement. Okay, and this is the Jabuski and Kruskals answer. So if we look at these two, then we can see that it's very natural by scaling. It's natural to introduce QH tilde in this form because there are H dependence in amplitude and time and position. So we just get, in order to get rid of this dependence, we introduce this function. And then by simple scaling from this one, we get this equation. Okay, and here delta H is discrete Laplacian on HC. Okay, and then and in particular, when V is a standard FPU potential, V prime is the sum of linear and quadratic term. So here there is V prime, but V prime is the sum of linear and quadratic sum terms. So it's very natural for PDE perspective. It's very natural to move the linear term to the left, and we organize the equation in this way. Okay, and then we can immediately see that this FPU is a discrete nonlinear wave equation. Okay, so wave type operator is on the left hand side. Okay, and then using the Duhamel formula, we may write this equation in this way. And here there are cosine and sine operators, and they are defined as a Fourier multiplier. I mean, on Fourier side, these operators is the multiplication of this symbol. Okay, but somehow these cosine and sines are complicated. So we separate cosine and sine using the identity we know for the trigonometric functions. Okay, so we can cosine, we can separate exponential operator here and there by separate. Okay, from cosine and sine operators in this Duhamel formula, and then separating the terms with plus thing, this one, and this one, and then we separate. Separating plus terms and minus terms, we end up with two coupled equation system for QH plus and QH minus in this way. Okay, and so the relation between QH and QH plus minus is this. If we sum it, we get QH. Okay, and this kind of reformulation is very standard for the nonlinear wave equation. Okay, there is nothing special, I think, and then finally we introduce a new function by putting some new operator, this one, and here partial H is the Fourier multiplier with symbol I cushy. Okay, and actually this kind of operator is related to the translation operator. So actually, if t is this discrete time, then we can easily see that this operator is translation operator in space. And actually, in Jabuski and Kruskals answer, there is translating factor. So somehow putting this additional thing corresponds to this translation up to scaling. Okay, so for this sense, in this sense, putting this additional operator, it makes sense. Okay, and then we write the equation for UH plus minus. and we call it a coupled FPU. So UH plus solves the equation with plus terms, but it's coupled equation because there is minus term, UH minus term here. Okay, and here SH plus minus is the propagator of this symbol. Okay, so this is the symbol for this linear propagators. Okay, we can write this operator using the Fourier transform, inverse Fourier transform. Okay, so we end up with finally we end up with this coupled system, and actually this coupled FPU is nothing but a reformulation. There is no difference. Just it is just a reformulation of FPU system, but we followed Jabuski and Kruskal's idea and their answers, and we also followed the standard way of reformulating the equation for the nonlinear wave equation. Okay, but so this is just a reformulation, but there is a good thing. The good thing is that this equation is much easier to see what's happening in the limit when h goes to 0 in a Fourier analysis perspective. Precisely, so there is a coupled term. So U plus equation satisfies the equation with pluses, but there is something with minus. But if U plus minus behaves linearly, I mean, this is true, roughly true, at least in a very short time. But if it behaves linearly, this coupled term can be UH minus plus minus behaves linearly, then this coupled term can be approximated by this one. I just replaced this nonlinear solution by the linear solution. Okay, and then if we write the integral representation for this solution, we get this, and in the end we get this. But a good thing is that these plane waves, the exponential function, has group velocity, which diverges to infinity as h goes to infinity. Okay, so it means that this oscillating term becomes very, spiky, and so it has a very good cancellation property. So in the end, this integral would vanish as h goes to 0. So motivated by this observation, it's very natural to introduce this decoupled FPU system by dropping the cross term, because we may expect that the drop term will disappear in the end. And then, okay. And then another observation we can get from this reformulated FPU is that the linear propagator. So this is the linear propagator, SH plus for the SH plus minus, the symbol for the linear propagator. But by direct calculation, we can see that this symbol would converges to cubic term as h goes to 0. So somehow this is the propagator we should have for the KdV equation. So actually we can expect that as h goes to 0, this linear propagator would be replaced by this area operator, area flow operator, and in the end we get the KdV equation. Okay. So far, so this is a quick summary. So so there are 3 equations appeared. The coupled FPU is just a reformulation of Fermi-Pasta-Ulam system, but based on the observation that this may disappear, we introduce the decoupled FPU, and And then this one can be, by the second observation, we may expect that this one would converge to the KdV equation. Okay. Okay. Then now let me show you the result. So in order to state the main theorem, we need the norms. So on the lattice domain, in the context of continuum limit, this is the natural definition of LP space, putting H in it. So I mean, putting this extra constant is very natural in consideration of Riemann sum. Okay, and the overlap space overlap norms are defined in a standard way. Okay, and what we proved is that when the initial data is bounded in overlap norm, then the solution to the coupled FPU converges to the solution to the decoupled equation with this rate. Okay, and then okay, so this is rigorous justification of the first observation, and then next, using the linear interpolation I mentioned earlier, we proved under some assumption, non-bound assumption on initial data, we proved the convergence from the decoupled FPU to KdV equation with this rate. So combining these two convergence theorem, this one, so coupled to decoupled FPU and decoupled FPU to KdV, we can conclude that the FPU solutions converges to KdV solutions as H goes to 0 for H 4/4 plus epsilon data. So somehow the regularity assumptions in previous result is reduced, and also some additional assumptions are relaxed here. Okay, here we only need the non-bound. Okay, and let me then let me briefly explain how we proved the key idea to prove this theorems. So actually, in order to prove the convergence continuum limit, one thing we need to be very careful is that we need inequalities which hold uniformly in H. So for instance, on lattice domain, there are many, actually more inequalities. So for instance, L infinity norm of U on lattice can be bounded by L1 norm like this, but this kind of inequality is not so useful in continuum limit because the constant diverges as H goes to 0. So we cannot use this kind of extra embedding. We need some inequality holding uniformly in H. Okay, and fortunately we have uniform overlap inequalities and uniform little Perry inequalities and so on. And also in order to handle low regularity data, we also need various uniform, dispersive, and smoothing estimates. And as I mentioned, in order to prove continuum limit, we need to know a better understanding for the nonlinear solution. But for that, we need a better understanding for linear solutions. Okay, so basically, for instance, for the proof, we need a local smoothing estimate for the linear FPU flow. So linear FPU flow is the Fourier multiplier of this oscillating term, but somehow we can prove the sort of local smoothing estimate. So here the key point is that on the left hand side there is additional derivative, so there is some smoothing estimate which resembles the local smoothing estimates for the airy flow for the KdV equation. It looks almost similar. And actually, the local smoothing estimate, the proof of local smoothing estimate is very simple. I don't want to, because of the limitation of time, I don't have time to go in detail, but somehow we can prove local smoothing estimate by Plancherel theorem, change of variable and Plancherel theorem. It's very short, even in this general case. But in our setting, our P is given by this guy, okay, and our P prime here can be the P prime here can be written in this way explicitly, but fortunately there is a very nice algebra for the trigonometric functions. We can actually compare this P prime with this guy. Actually, this guy is the multiplier for the derivative. So somehow, so here what this says is that we can gain some additional thing in general, but the problem is whether this guy is comparable with this derivative operator. But in this FPU case, there is a good algebra for the trigonometric functions. We can actually compare this guy with this trigonometric function so that we can prove local smoothing estimates for the FPU flow. But I want to say that this is not obvious in general. Indeed, for the Schrödinger equation, I mean, in PDE case, the problem on R, 1D linear Schrödinger flow has similar local smoothing estimates, but in discrete case, we don't have it actually, because this P prime, I mean, the correct for the discrete linear flow, the corresponding P is this guy, but P prime can be 0 in the integral domain, in the integral. So in this case, the P prime cannot be comparable with the derivative operator because in high frequency it is like 0. So it is shown that the local smoothing is not available for the discrete Schrödinger equation, but for the FPU case, there is a good algebra so that we have it. And similarly, we can also prove some bilinear estimate. So this is a famous bilinear estimate in the theory of dispersive PDE introduced by Bruggen, and actually for the linear FPU flow, we can actually recover similar bilinear estimate for bilinear estimates, and then applying and also this the proof of these estimates also heavily depends on the good algebra of FPU symbol. Okay, and then we also proved some other estimates for the linear FPU flows, maximal function estimates and Strickhardt estimates, and then applying all of good linear estimates, we got good bounds for the nonlinear solutions, and then using this additional information, we proved the continuum limit, the convergence from FPU to KdV equation. Okay. And this is the end of my talk, and thank you for your attention.
Thanks, Younghun, for a very interesting talk. Are there any questions and comments? Younghun, your solution is local in time.
Yes.
And this is what you can obtain because you are using the Hamel formula, but can you use other arguments to show global existence, or it's not possible?
So actually, we try to prove global in time convergence, but we could do that for the nonlinear Schrödinger equation because the energy is in H1 level. So there is some, we can use the energy conservation law to prove, to obtain global in time convergence. And we could do that for the nonlinear Schrödinger equation. But for this problem, unfortunately, FPU has, as I know, FPU has some conservation law which only controls L2 norm. But in this case, in our result, we couldn't prove the convergence in L2 level. So we cannot use the energy conservation law, I think. So there is some hope if we can reduce the regularity assumption in the theorem to obtain global in time convergence. But at this moment, we do not know how to do that.
Thank you. Are there other questions, comments? If not, then I will close the meeting and everyone is welcome to attend the coffee break. Probably everyone received an email with the link to coffee break in a few minutes time. So thanks again, Younghun, for this interesting talk, and see you in a few minutes.
Okay, thank you very much.
Okay, bye.
Bye.